Hello, welcome to Maps of Math. In this video, I'm going to say what is a group, or answer what is a group. So a group is a one object category, and with the special restriction where every morphism has to be an isomorphism. So if you don't know what categories are, check them out. Kind of important to understand what groups are. Although I'll say this isn't the standard treatment, but I think it's probably the better definition, or at least as good. They're equivalent, but I like this definition more. So technically, we can take any object as the one object. We just call it star. And then the elements of the group are the arrows or morphisms. When I say elements, it's not elements of the set, but usually think of when you write groups out, you'll have E for the identity, you'll have whatever the names of them are. Well, when you're doing the categorical definition of groups, then what are called the elements usually are they are elements, actually. I guess they're elements of the home set. So, if I have home, we'll call it G for the group, star, comma, star. Well, then, if I take any F and G in the home set, the composition, that's what the product is in the group. And I'm assuming here it's not necessarily abelian, so this is non-commutative. But I guess you could have commutative, in which case you might use additive notation instead of the composition like this. There is a identity morphism that already exists, and for every F in home, there is an F inverse because every morphism is an isomorphism. So these combined do give us the normal group axioms. It is best to think of the object as being meaningful and have the arrows actually be a transformation of it. So just to give an example, we could have the objects of G, let's say there are these three different slots, A, B, C, and the home set can be all the bijections on this. So if you're used to the permutation notation, there's the identity, swapping 1 and 2, swapping 1 and 3, swapping 2 and 3, cycling through 1, 2, 3, and cycling through 1, 3, 2. That's if you're used to permutation notation. Obviously here the group then is the permutations on 3 letters or 3 objects, whatever. As a different example, we could take the square, label the corners A, B, C, D, pretend that's a square. We'll call that our star, and then home G star comma star is just going to be the symmetries of the square. And so that would consist of the identity, 3 different rotations, so 90, 180, 270. And then these are the different reflections. So you have the X reflection, the Y reflection this way, and then the 2 diagonal reflections. So this is the dihedral group on symmetries of the square, dihedral D4. All right, that's it for this. I'll probably use some more group theory and get into it, but that's all groups are. Groups are given object, transformations of that object, and then obviously if you have isomorphisms between 2 different groups, so between these one object categories, which actually think about what that would entail, because those isomorphisms, if these are one object categories, those have to be themselves functors. So those are going to be the same group. Okay, I'll stop there. Hope you are well.